Maybe we should begin even before that at the very base layer of the Wolfram Physics Project. Maybe you can give a broad overview once again, really quick about this hypergraph model. And
Yes.
also, what is it, a year and a half ago since you've brought this project to the world? What is
Yes.
the status update? What are all the beautiful ideas you have come across? What are the interesting things you can
Oh,
sort of mention?
I mean, it's a frigging Cambrian explosion. I mean, it's crazy. I mean, there are all these things which I've kind of wondered about for years, and suddenly there's actually a way to think about them.
Mhm.
And I really did not see. I mean, the real strength of what's happened, I absolutely did not see coming. And the real strength of it is we've got this model for physics, but it turns out it's a foundational kind of model that's a different kind of computation-like model that I'm kind of calling the sort of multi-computational model.
Mhm.
And that kind of model is applicable not only to physics, but also to lots of other kinds of things. And one reason that's extremely powerful is because physics has been very successful. So we know a lot based on what we figured out in physics. And if we know that the same model governs physics and governs, I don't know, economics, linguistics, immunology, whatever, we know that the same kind of model governs those things. We can start using things that we've successfully discovered in physics and applying those intuitions in all these other areas. And that's pretty exciting and very surprising to me. And in fact, it's kind of like in the original story of sort of you go and you explain why is there complexity in the natural world, then you realize, well, there's all this complexity, there's all this computational irreducibility, there's a lot we can't know about what's going to happen. It's kind of a very confusing thing for people who say, science has nailed everything down. We're going to, based on science, we can know everything.
Mhm.
Well, actually, there's this computational irreducibility thing right in the middle of that, thrown up by science, so to speak. And then the question is, well, given computational irreducibility, how can we actually figure out anything about what happens in the world? Why are we able to predict anything? Why are we able to sort of operate in the world? And the answer is that we sort of live in these slices of computational reusability that exist in this kind of ocean of computational irreducibility. And it turns out that it seems that it's a very fundamental feature of the kind of model that seems to operate in physics and perhaps in a lot of these other areas, that there are these particular slices of computational reducibility that are relevant to us. And those are the things that both allow us to operate in the world
Mhm.
and not just have everything be completely unpredictable, but they're also things that potentially give us what amount to sort of physics-like laws
Mhm.
in all these other areas. So that's been sort of an exciting thing. But I would say that in general for our project, it's been going spectacularly well. I mean, it's very honestly, it wasn't something I expected to happen in my lifetime. I mean, it's something where and in fact, one of the things about it, some of the things that we've discovered are things where I was pretty sure that wasn't how things worked.
Mhm.
And turns out I'm wrong. And in a major area in mathematics, I'd be realizing that something I've long believed. We can talk about it
Mhm.
later. Just really isn't right.
Mhm.
But I think that the thing that so what's happened with the physics project? I mean, it's it can explain a little bit about how the model works. But basically,
We can maybe ask you the following question. So it's easy through words to describe how cellular automata works. You've explained this, and it's the fundamental mechanism by which you, in your book A New Kind of Science, explored the idea of complexity and how to do
mhm.
science in this world of reducible islands and general irreducibility. Okay, so how does the model of hypergraphs differ from cellular automata, and how does the idea of multi-computation differ? Like maybe
Okay,
that's a way to describe
all
it.
right, we're yeah, right. This is my life is like all of our lives, something of a story of computational irreducibility.
Yes.
And, it's been going for a few years now. So it's always a challenge to kind of find these appropriate pockets of reducibility. But
Mhm.
let me see what I can do.
Great.
So I mean, first of all, let's talk about physics, first of all.
Hmm.
And, a key observation that one of the starting point of our physics project is things about what is space? What is the universe made of? And, ever since Euclid, people just sort of say space is just this thing where you can put things at any position you want. and they're just points, and they're just geometrical things that you can just arbitrarily put at different coordinate positions. Sort of the first thing in our physics project is the idea that space is made of something. Just like water is made of molecules, space is made of kind of atoms of space. And the only thing we can say about these atoms of space is they have some identity. It's this atom as opposed to this atom. And, you could give them, if you were a computer person, you give them UUIDs or something. But,
Yes.
But that's all there is to say about them, so to speak. And then all we know about these atoms of space is how they relate to each other. So we say these three atoms of space are associated with each other in some relation. So you can think about that as, what atom of space is friends with what other atom of space. Mm-hmm. You can build this essentially friend network of the atoms of space. And the sort of starting point of our physics project is that's what our universe is. It's a giant friend network of the atoms of space. And so how can that possibly represent our universe? Well, it's like in something like water, there are molecules bouncing around, but on a large scale, that produces fluid flow, and we have fluid vortices, and we have all of these phenomena that are sort of the emergent phenomena from that underlying kind of collection of molecules bouncing around. Mm-hmm. And by the way, it's important that collection of molecules bouncing around have this phenomenon of computational irreducibility. That's actually what leads to the second law of thermodynamics, among other things. And that leads to the sort of randomness of the underlying behavior, which is what gives you something which on a large scale seems like it's a smooth, continuous type of thing. And so first thing is space is made of something. It's made of all these atoms of space connected together in this network. And then everything that we experience is sort of features of that structure of space. So, when we have an electron or something, or a photon, it's some kind of tangle in the structure of space, much like kind of a vortex in a fluid would be just this thing that is, it can actually, the vortex can move around, it can involve different molecules in the fluid, but the vortex still stays there.
And if you zoom out enough, the vortex looks like an atom itself, like a basic element.
Yes.
So there's the levels of abstraction. If you squint and kind of blur things out, it looks like at every level of abstraction, you can define what is a basic individual entity.
Yes, but in this model, there's a bottom level.
Yeah.
There's an elementary length. Maybe
that
it's 10 to the minus
discrete.
100, 10 to the minus 100 meters, let's say, which is really small. A proton is 10 to the minus 15 meters. The smallest we've ever been able to sort of see with a particle accelerator is around 10 to the minus 21 meters. So, if we don't know precisely what the correct scale is, but it's perhaps over the order of 10 to the minus 100 meters. So it's pretty small. But that's the end. That's what things are made of.
What's your intuition where the 10 to the minus 100 comes from? What's your intuition about this scale?
Well, okay, so there's a calculation which I consider to be somewhat rickety, okay, which has to do with comparing. So there are various fundamental constants. There's the speed of light. The speed of light, once you know the elementary time, the speed of light tells you the conversion from the elementary time to the elementary length. Then there's the question of how do you convert to the elementary energy, and how do you convert to between other things. And the various constants we know. We know the speed of light. We know the gravitational constant. We know Planck's constant in quantum mechanics. Those are the three important ones. And we actually know some other things. We know things like the size of the universe, the Hubble constant, things like that. And essentially, this calculation of the elementary length comes from looking at these sort of combination of those. Okay, so the most obvious thing, people have sort of assumed that quantum gravity happens at this thing, the Planck scale, 10 to the minus 34 meters, which is the sort of the combination of Planck's constant and the gravitational constant, the speed of light, that gives you that kind of length. Mm-hmm. Turns out in our model, there is an additional parameter, which is essentially the number of simultaneous threads of execution of the universe, mm-hmm. which is essentially the number of sort of independent quantum processes that are going on. And that number, let's see if I remember that number is 10 to the 170, I think. And so it's a big number. Mm-hmm. But that number then connects, sort of modifies what you might think from all these Planck units to give you the things we're giving. And there's been sort of a mystery actually there's a more technical physics thing that the Planck mass, the Planck energy Planck energy is actually surprisingly big. The Planck length is tiny, 10 to the minus 34 meters. Planck time, 10 to the minus 43 meters, I think, seconds, I think. But the Planck energy is like the energy of a lightning strike, okay, which is pretty weird. In our models, the actual elementary energy is that divided by the number of sort of simultaneous quantum threads, and it ends up being really small too. And that sort of explains that mystery that's been around for a while about how Planck units work. But whether that precise estimate is right, we don't know yet. I mean, that's one of the things that's sort of been a thing we've been pretty interested in, is how do you see through, how do you make a gravitational microscope that can kind of see through to the atoms of space? How do you get in fluid flow, for example, if you go to hypersonic flow or something, you've got a Mach 20, space plane or something, it really matters that there are individual molecules hitting the space plane, not a continuous fluid. The question is, what is the analog of hypersonic flow for things about the structure of space-time? And it looks like a rapidly rotating black hole, right at the sort of critical rotation rate, it looks as if that's a case where essentially the structure of space-time is just about to fall apart, and you may be able to kind of see the evidence of sort of discrete elements. You may be able to kind of see there the sort of gravitational microscope of actually seeing these discrete elements of space. And there may be some effect in, for example, gravitational waves produced by rapidly rotating black hole, that in which one could actually see some phenomenon where one can say, yes, these don't come out the way one would expect based on having a continuous structure of space-time. It is something where you can kind of see through to the discrete structure. We don't know that yet.
So can you maybe elaborate a little bit deeper how a microscope that can see to 10 to the minus 100, how rotating black holes and presumably the detailed, accurate detection of gravitational waves from such black holes can reveal the discreteness of space?
Okay, first thing is, what is a black hole? Actually, we need to go a little bit further in the story of what space-time is, because I explained a little bit about what space is, but I didn't talk about what time is. And that's sort of important in understanding space-time, so to speak.
Mm-hmm. And your sense is both space and time in the story are discrete.
Absolutely. But it's a complicated story.
Yes.
And needless to say.
Well, it's simple at the bottom.
It's very simple at the bottom. It's very, in the end, it's simple but deeply abstract, and something that is simple in conception, but kind of wrapping one's head around what's going on is pretty hard. Mm-hmm. But so first of all, we have this. So I've described these kind of atoms of space and their connections. You can think about these things as a hypergraph. A graph is just you connect nodes to nodes, but a hypergraph you can have sort of not just individual friends to friends, but you can have these triplets of friends or whatever else. It's and so we're just saying, and that's just the relations between atoms of space are the hyperedges of the hypergraph. And so we got some big collection of these atoms of space, maybe 10 to the 400 or something in our universe, and that's the structure of space. And every feature of what we experience in the world is a feature of that hypergraph, that spatial hypergraph. So then the question is, well, what does that spatial hypergraph do? Well, the idea is that there are rules that update that spatial hypergraph. And, in a cellular automaton, you've just got this line of cells, and you just say at every time step, you've got fixed time steps, fixed array of cells. At every step, every cell gets updated according to a certain rule. Mm-hmm. And that's kind of that's the way it works. Now, in this hypergraph, it's sort of vaguely the same kind of thing. We say every time you see a little piece of hypergraph that looks like this, update it to one that looks like this. Mm-hmm. So it's just keep rewriting this hypergraph. Every time you see something that looks like that anywhere in the universe, it gets rewritten. Now, one thing that's tricky about that, which we'll come to, is this multi-computational idea, which has to do with you're not saying in some kind of lockstep way, do this one, then this one, then this one. It's just whenever you see one you can go ahead and do it. And that leads one not to have a single thread of time in the universe. Because if you knew which one to do, you would just say, okay, we do this one, then we do this one, then we do this one. But if you say just do whichever one you feel like, you end up with these multiple threads of time, these kind of multiple histories of the universe, depending on which order you happen to do the things you could do in.
So it's fundamentally asynchronous and parallel.
Yes. Yes.
Which is very uncomfortable for the human brain that seeks for things to be sequential and synchronous.
Right. Well, I think that this is part of the story of consciousness, is I think the key aspect of consciousness that is important for sort of parsing the universe is this point that we have a single thread of experience.
Right.
We have a memory of what happened in the past. We can say something, predict something about the future, but there's a single thread of experience. And it's not obvious it should work that way. I mean, we've got 100 billion neurons in our brains, and they're all firing in all kinds of different ways. But yet our experience is that there is this single thread of time that goes along. Mm-hmm. And I think that, one of the things I've kind of realized with a lot more clarity in the last year is the fact that we conclude that the universe has the laws it has is a consequence of the fact that we have consciousness the way we have consciousness. And so I mean, just to go on with kind of the basic setup, mm-hmm. It's so we got this spatial hypergraph. It's got all these atoms of space. They're getting these little clumps of atoms of space are getting turned into other clumps of atoms of space, and that's happening everywhere in the universe all the time. And so one thing that's a little bit weird is there's nothing permanent in the universe. The universe is getting rewritten everywhere all the time. Mm-hmm. And if it wasn't getting rewritten, space wouldn't be knitted together. That is, space would just fall apart. There wouldn't be any way in which we could say this part of space is next to this part of space. Mm-hmm. One of the things that people were confused about back in antiquity, the ancient Greek philosophers and so on, is how does motion work? How can it be the case that you can take a thing that we can walk around and it's still us when we walked, mm-hmm. A foot forward, so to speak? And in a sense, with our models, that's again a question, because it's a different set of atoms of space. When I move my hand, it's moving into a different set of atoms of space. Mm-hmm. It's having to be recreated. It's not, the thing itself is not there. It's being continuously recreated all the time. Mm-hmm. Now, it's a little bit like waves in an ocean, vortices in a fluid, which again, the actual molecules that exist in those are not what define the identity of the thing. Mm-hmm. But it's a little bit, this idea that there can be pure motion, that it is even possible mm-hmm. for an object to just move around in the universe and not change, it's not self-evident that such a thing should be possible. And that is part of our perception of the universe, is that we parse those aspects of the universe where things like pure motion are possible. Now, pure motion, even in general relativity, the theory of gravity, pure motion is a little bit of a complicated thing. I mean, if you imagine your average, teacup or something approaching a black hole, it is deformed and distorted by the structure of space-time. Mm-hmm. And to say, is it really pure motion? Is it that same teacup that's the same shape? Well, it's a bit of a complicated story. Mm-hmm. And this is a more extreme version of that. So anyway, the thing that's happening is we've got space, we've got this notion of time. So time is this rewriting of the hypergraph. Mm-hmm. And one of the things that's important about that, time is this sort of computationally irreducible process. There's something, time is not something where, in kind of the mathematical view of time, tends to be, time is just a coordinate. We can, slide a slider, turn a knob, and we'll change the time that we've got in this equation. Mm-hmm. But in this picture of time, that's not how it works at all. Time is this inexorable, irreducible kind of set of computations that go from where we are now to the future. But so the thing, and one of the things that is, again, something one sort of has to break out of, is your average trained physicist like me says, space and time are the same kind of thing. They're related by, the Poincare group and Lorentz transformations and relativity and all these kinds of things. And, space and time, there are all these kind of sort of folk stories you can tell about why space and time are the same kind of thing. In this model, they're fundamentally not the same kind of thing. Space is this kind of sort of connections between these atoms of space. Time is this computational process. So the first sort of surprising thing is, well, it turns out you get relativity anyway. And the reason that happens, there are a few bits and pieces here which one has to understand, but the fundamental point is, if you are an observer embedded in the system that are part of this whole story of things getting updated in this way and that, there's sort of a limit to what you can tell about what's going on. And really, in the end, the only thing you can tell is what are the causal relationships between events. So an event in this sort of an elementary event is a little piece of hypergraph got rewritten. And that means a few hyperedges of the hypergraph were consumed by the event, and you produce some other hyperedges. And that's an elementary event. And so then the question is, what we can tell is kind of what the network of causal relationships between elementary events is. That's the ultimate thing, the causal graph of the universe. And it turns out that, well, there's this property of causal invariance that is true of a bunch of these models, and I think is inevitably true for a variety of reasons, that makes it be the case that it doesn't matter kind of if you are sort of saying, well, I've got this hypergraph and I can rewrite this piece here and this piece here, and I do them all in different orders. When you construct the causal graph for each of those orders that you choose to do things in, you'll end up with the same causal graph. And so that's essentially why, that's in the end why relativity works. It's why our perception of space and time is as having this kind of connection that relativity says they should have. And that's kind of how that works.
I think I'm missing a little piece. If we can go there again, you said the fact that the observer is embedded in this hypergraph. What's missing? What is the observer not able to state about this universe of space and time?
If you look from the outside, you can say, "Oh, I see this. I see this particular place was updated, and then this one was updated, and I'm seeing which order things were updated in." But the observer embedded in the universe doesn't know which order things were updated in, because until they've been updated, they have no idea what else happened. So the only thing they know is the set of causal relationships. Let me give an extreme example. Let's imagine that the universe is a Turing machine. Turing machines have just this one update head which does something, and otherwise the Turing machine just does nothing, right? And the Turing machine works by having this head move around and do its updating, just where the head happens to be. The question is, could the universe be a Turing machine? Yes. Could the universe just have a single updating head that's just zipping around all over the place? You say that's crazy because, I'm talking to you, you seem to be updating, I'm updating, etc. But the thing is, there's no way to know that, because if there was just this head moving around, it's like, okay, it updates me, but you're completely frozen at that point. Until the head has come over and updated you, you have no idea what happened to me. And so if you sort of unravel that argument, you realize the only thing we actually can tell is what the network of causal relationships between the things that happened were. We don't get to know from some sort of outside sort of God's eye view of the thing. We don't get to know what sort of from the outside what happened. We only get to know sort of what the set of relationships between the things that happened actually were.
Yeah, but if I somehow record like a trace of this, I guess would be called multi-computation, can't I then look back in the
Where do you
causal
record the trace?
You place throughout the universe, like a log that records in my own pocket in this hypergraph. Can't I, like, realizing that I'm getting an outdated picture, can't I record?
See, the problem is, and this is where things start getting very entangled in terms of what one understands. The problem is that any such recording device is itself part of the universe.
Yeah.
So you never get to say, let's go outside the universe and go do this. And that's why, I mean, lots of the features of this model and the way things work end up being a result of that.
So, but what, I guess, on a human level, what is the cost you're paying? What are you missing from not getting an updated picture all the time? Okay, I understand what you're just saying.
Yeah, right.
But how does consciousness emerge from that? Like how, like what are the limitations of that observer? Okay. I understand you're getting a delayed picture.
There's a bunch of limitations of the observer, I think. Yeah. Maybe just explain something about quantum mechanics, because that maybe is an extreme version of some of these issues, which helps to kind of motivate why one should sort of think things through a little bit more carefully. So one feature of this, so in standard physics, like high school physics, you learn, the equations of motion for a ball. And it says you throw the ball this angle, this velocity, things will move in this way, and there's a definite answer. Right? The key story of quantum mechanics is there aren't definite answers to where does the ball go. There's kind of this whole sort of bundle of possible paths, and all we say we know from quantum mechanics is certain probabilities for where the ball will end up. Okay, so that's kind of the core idea of quantum mechanics. So in our models, quantum mechanics is not some kind of plug-in add-on type thing. Mm-hmm. You absolutely cannot get away from quantum mechanics, because as you think about updating this hypergraph, there isn't just one sequence of things, one definite sequence of things that can happen. There are all these different possible update sequences that can occur. You could do this, piece of the hypergraph now, and then this one later, and et cetera, et cetera, et cetera. All those different paths of history correspond to these quantum paths in quantum mechanics, these different possible quantum histories. And one of the things that's kind of surprising about it is they branch. There can be a certain state of the universe, and it could do this or it could do that, but they can also merge. There can be two states of the universe, which the next state they produce is the same for both of them.
Yeah. And
that process of branching and merging is kind of critical. And the idea that there can be merging is critical and somewhat non-trivial for these hypergraphs, because there's a whole graph isomorphism story, and there's a whole very elaborate set of mathematics.
That's where the causal invariance comes in.
Yes, among other things. Right. Okay. Yes. That's so then what happens is that what one's seeing. Okay, so we've got this thing, it's branching, it's merging, et cetera, et cetera, et cetera. Okay, so now the question is, how do we perceive that? Why don't we notice that the universe is branching and merging? Mm-hmm. Why is it the case that we just think a definite set of things happen? Mm-hmm. Well, the answer is we are embedded in that universe, and our brains are branching and merging too. Mm-hmm. And so what quantum mechanics becomes a story of is, how does a branching brain perceive a branching universe? Mm-hmm. And the key thing is, as soon as you say, I think definite things happen in the universe, that means you are essentially conflating lots of different paths of history. You're saying, actually, as far as I'm concerned, because I'm convinced that definite things happen in the universe, all these paths of history must be equivalent. Now, it's not obvious that that would be a consistent thing to do. It might be you say all these paths of history are equivalent, but by golly, moments later, that would be a completely inconsistent point of view. Everything would have, gone to hell in different ways. The fact that that doesn't happen is, well, that's a consequence of this causal invariance thing, and the fact that that does happen a little bit is what causes little quantum effects. Mm-hmm. And that if that didn't happen at all, there wouldn't be anything that sort of is like quantum mechanics. It would be, quantum mechanics is kind of like in this kind of this bundle of paths. It's a little bit like what happens in statistical mechanics and fluid mechanics, whatever, that most of the time you just see this continuous fluid. You just see the world just progressing in this kind of way that's like this continuous fluid. But every so often, if you look at the exact right experiment, you can start seeing, well, actually, it's made of these molecules where they might go that way or they might go this way, and that's kind of quantum effects. Mm-hmm. And so this kind of idea of we're sort of embedded in the universe, this branching brain is perceiving this branching universe, and that ends up being sort of a story of quantum mechanics. That's part of the whole picture of what's going on. But I mean, to come back to sort of what is the story of consciousness? So in the universe, we've got, whatever it is, 10 to the 400 atoms of space. They're all doing these complicated things. It's all a big, complicated, irreducible computation. The question is, what do we perceive from all of that? Mm-hmm. And the answer is that we are parsing the universe in a particular way. Let me again go back to the gas molecules analogy. In the gas in this room, there are molecules bouncing around in all kinds of complicated patterns, mm-hmm. but we don't care. All we notice is there's, the gas laws are satisfied. Maybe there's some fluid dynamics. These are kind of features of that assembly of molecules that we notice, and then lots of details we don't notice.
When you say we, do you mean the tools of physics, or do you mean literally the human brain and its perception system?
Well, okay, so the human brain is where it starts, but we've built a bunch of instruments to do a bit better than the human brain, but they still have many of the same kinds of ideas. Their cameras and their pressure sensors and these kinds of things. They're not, at this point, we don't know how to make fundamentally qualitatively different sensory devices.
Right.
And
so it's always just an extension of the conscious experience, even
or our sensory experience.
Sensory experience, but sensory experience that's somehow intricately tied to consciousness.
Right. Well, so one question is, when we are looking at all these molecules in the gas, and there might be 10 to the 20th molecules in some little box or something, it's like, what do we notice about those molecules? So one thing that we can say is we don't notice that much. We are computationally bounded observers. We can't go in and say, okay, they're 10 to the 20th molecules, and I know that I can sort of decrypt their motions and I can figure out this and that. It's like, I'm just going to say what's the average density of molecules. And so one key feature of us is that we are computationally bounded. And that when you are looking at a universe which is full of computation and doing huge amounts of computation, but we are computationally bounded, there's only certain things about that universe that we're going to be sensitive to. We're not going to be, figuring out what all the atoms of space are doing, because we're just computationally bounded observers, and we are only sampling these small set of features. So I think the two defining features of consciousness I would say that the sort of the preamble to this is, for years, because I've talked about sort of computation and fundamental features of physics and science, people ask me, so what about consciousness? Mm-hmm. And for years, I've said, I have nothing to say about consciousness. And, I've kind of told this story, you talk about intelligence, you talk about life. These are both features where you say, what's the abstract definition of life? We don't really know the abstract definition. We know the one for life on Earth. It's got RNA, it's got cell membranes, it's got all this kind of stuff. Similarly, for intelligence, we know the human definition of intelligence, but what is intelligence abstractly? We don't really know. And so what I've long believed is that sort of the abstract definition of intelligence is just computational sophistication. That is, that as soon as you can be computationally sophisticated, that's kind of the abstract version, the generalized version of intelligence. Mm-hmm. So then the question is, what about consciousness? And what I sort of realized is that consciousness is actually a step down from intelligence. That is, that you might think, consciousness is the top of the pile. Mm-hmm. But actually, I don't think it is. I think that there's this notion of kind of computational sophistication, which is the generalized intelligence. Mm-hmm. But consciousness has two limitations, I think. One of them is computational boundedness. That is, that we're only perceiving a sort of computationally bounded view of the universe. And the other is this idea of a single thread of time. Mm-hmm. That is, that and in fact, we know neurophysiologically our brains go to some trouble to give us this one thread of attention, so to speak. Mm-hmm. And it isn't the case that, in all the neurons in our brains that in at least in our conscious, the correspondence of language, in our conscious experience, we just have this single thread of attention, single thread of perception. And maybe there's something unconscious that's bubbling around, that's the kind of almost the quantum version of what's happening in our brain, so to speak. We've got the classical flow of what we are mostly thinking about, so to speak. But there's this kind of bubbling around of other paths that is all those other neurons that didn't make it to be part of our sort of conscious stream of experience.